Alright, so in a previous video, we derived the steady state model of the induction machine, and in this video we're going to look at how we can control the induction machine, since control is what this is all about. I mean, there's no purpose of running an induction machine if you can't control it, or any machine for that matter. If you can't control what you want the machine to do, or what the machine is doing, then there's really no point of doing anything. So we have these equations. I've labeled them 1, 2, 3, and 4, and we derived them in a previous video. And if you haven't seen that video, I've linked in the description below so you can familiarize yourself with that. But you'll notice based on these equations that there is an issue here in that the equations are coupled. So the currents IS and IR are coupled to one another. So the control in this case becomes complicated because what you have is if one of the currents changes, the other one depends on that current. So there's a relationship between the two. So now in control theory, the way we circumvent these issues is we usually introduce some new fictitious variable and define it, and then we manipulate that new variable in order to decouple the entire control. So we're going to do exactly that here as well. So what are we going to introduce? Let's introduce a current. Let's introduce a current called IMR. And this is going to be a vector as well. And let's say it's defined as lambda r prime divided by Lm. And this means that IMR, the current phasor, I guess you can call it, is equal to some magnitude IMR, e to the j rho. And IMR, IMR is obviously the magnitude of the vector, and it rotates at a speed of the time derivative of rho. Now, based on equation 2 and this new definition that we've established, we can say, let's say 2. So from 2, we can establish that this is just a substitution. So I say Lm IMR is equal to Lr prime. Oh, sorry, Lr IR prime, I should say, plus Lm IS. And if you recall, Lr can be expressed in terms of Lm using sigma r. And so you can rewrite this whole thing as IMR equals 1 plus sigma r IR prime plus IS. And why don't we call this equation 6? Okay, next, what we can do is we can say that also, I mean, I guess if you wanted to, you can rearrange this in another form because this might be easier to manipulate later on. So why don't we rearrange this in another format to say that IR prime is equal to minus IS plus IMR e to the j rho divided by 1 plus sigma r. And we know that rho is equal to the integral of omega dt, and this omega is the supply frequency. So this is the frequency that you're actually driving the motor with. Because again, these machines, because you're controlling the speed, you're essentially controlling the frequency of operation of the signal or the voltage or the current, whatever you're supplying to the machine. So then what you can do is you can use this and you can rewrite then the torque equations. So if you remember, the torque equation was the imaginary part of 3 over 2 times Lm. There was this giant well, not giant, but there was the product of Is and Ir, and then you had like the conjugate and all that kind of stuff. But the torque basically can be rewritten as Te 3/2 Lm, and this is the imaginary part of Is times minus Is, and this probably explains why, or well, this is the reason why we rewrote the equation above for IR, is because we want to use it in this expression here. So IMR e to the j rho over 1 plus sigma r, and this is conjugate. Now I mean, as you've probably noticed so far, this is going to be a fairly mathematical topic because this is a control exercise at the end of the day. Control requires a lot of mathematics. So now, if you simplify this, I mean, you can take these terms inside and you can apply the conjugates to this, and you can simplify the entire expression. And if you do so, you'll find that, I mean, rather than go through the entire steps, I mean, I'll leave that to you because it's simple arithmetic. Well, I guess it's complex arithmetic and not that simple, but that's a math joke for those of you that didn't catch it. In any case, this is Lm over 1 plus sigma r, IMR, imaginary part of is e to the minus j rho. And this is what we call equation 7, and this should be a vector. So what this means is this is a vector, or a phasor, let's call it. And this is a phasor that's rotating in space with a phase of rho and an angular frequency of the time derivative of rho, essentially. So this is the same rho here. So it's rotating at the supply frequency, because this is the relationship between omega and rho. So this is the phasor rotating in space at a frequency of omega, let's say. So now what we can do is we can take this quantity here, and we can regard it as an expression of the stator current Is on an orthogonal coordinate system that we call the DQ frame. Now, some of you might be familiar with the DQ frame if you've studied any drives or power electronics in the past. In three-phase circuits, we do, so in our standard, and I'll link a video in the description where we go into more detail, but for now, I mean, it suffices to say that in a standard system, or a standard three-phase system, you have three signals that are like this, right? So you have phase, let's say A, B, and C. But what we do is you can project these three signals onto a two-dimensional plane that we call alpha and beta. And so this is usually the real and the imaginary component, we can say. But then you can take it one step further, and you can kind of rotate this orthogonal, because they call this orthogonal frame because it's a orthogonal frame, literally. And what you can do then, you can take the alpha and the beta components. So you have alpha and you have beta, but then what you can do is you can start to rotate that frame, let's say, at an angle. And that angle, or that speed, I should say, because you rotate it at a speed, that speed is basically the time derivative of rho, and we call this the DQ frame. So you can basically decompose any three-phase signals, and the reason I'm saying three-phase is because these induction machines are usually three-phase machines. And so in a case like that, it's useful to, and it's more convenient when doing the analysis, to project it onto a DQ axis rather than consider it with an ABC or even an alpha beta, because it allows for easier control at the end of the day. So as I was saying, the expression, or sorry, this term, this green highlighted term here, this term here, can be regarded as a projection, or the expression, I guess, of Is on an orthogonal coordinate system. And we call that system the DQ frame. Essentially, we say it's a rotated version of the alpha beta frame, and the angle of rotation is rho, and the speed at which this thing rotates, because usually this DQ frame is also rotating, but you make the DQ frame is usually set to rotate at the same speed as the phasor is. So that's why everything is in terms of e to the j, or everything has the term e to the j rho. So what does this actually mean in terms of what's really going on and all this? Because those were really rough sketches as to what the situation is. So you have, let's say, your alpha and your beta frame, and then on top of that you have, let's say, change the color, but I guess we didn't. On top of that you have your DQ. So this is DQ, not Dairy Queen, but DQ for direct and quadrature. And these are 90 degrees, I guess, relative to one another. And so any current like this, let's say this current, or any, I guess, phasor, it doesn't have to be a current, it's any phasor. Any phasor, let's say this is Is in this case, because that's what we're dealing with. And this is the stator current, right? So any current can obviously be, or any phasor, I keep saying current, any phasor can be decomposed into these two components. And so you have one component that would be here, and you have one component that would be here. And so this component on this side, we call it ISD, and that's the D-axis component. And this is ISQ. Okay? And now we say that ISD is equal, or I guess essentially you can say ISD is IMR, and this is lambda R prime over LM. So that's what's going on here. So, I mean, if you want to put it mathematically, I guess we can say that IS e to the minus j rho, and this is a vector, is equal to ISD plus j ISQ. And another, I guess, an extension of this is that the imaginary part of IS e to the minus j rho, sorry, positive j rho, no, minus j rho. Minus j rho? Minus j rho. Minus j rho is equal to ISQ. And that's what you can see here. That's what this axis is, because the alpha is the real component and beta is the imaginary. So if you take it one step further, you can find that this imaginary component is ISQ. Then if you express all of this using the DQ frame, you can say that TE, the torque, is equal to 3 over 2 LM over 1 plus sigma R IMR ISQ. And so now you have a fairly clean equation, and we'll call this equation 8. And so now the torque is directly controllable in the same way that it was in a DC machine. So this is what we have for the induction machine. And if you recall, in a DC machine, so a DC machine torque, we said that Tm is equal to K phi IA. So now if you control ISQ or you control IMR, whichever one we choose to control directly, we can use that single current to control the torque directly. There's no coupled variables anymore. We've decoupled that through this sort of manipulation. So now how do we control IMR? Because that's what we're going to do. So we can say control of IMR is based on equation 4. So equation 4 all the way at the top, if you go back to the top or the beginning of the video, equation 4 says that d lambda r prime over dt is equal to VR prime minus RR IR prime plus j omega r lambda r prime. Right? And so we're going to assume that we're using a squirrel cage motor. And so in a squirrel cage motor, you have VR as 0 because by nature of the way that it's connected. And you know that lambda r prime is equal to LM IMR, right? We established this at the beginning. And this, therefore, is equal to LM IMR e to the j rho. And this is the angle, I guess you can say, of lambda r prime. So now what you can do is you can take this and substitute that into the equation above, right? So if we do that, well, we're really only going to substitute it on the left side, and then we can simplify it all. We'll substitute it. We'll substitute on the left side, and then we'll simplify it, and we'll see what we get after. So if you substitute that into the equation above, you get d over dt lambda r prime e to the j rho, and this is equal to minus RR times I, or minus IS. Maybe we put a bracket here because it'll make it clearer. Minus RR minus IS plus lambda r prime over LM e to the j rho over 1 plus sigma r. And then you have your speed voltage term here, like this. And so what we've done is we replaced this with its magnitude and its phase. And so what I'm doing in this case, I guess that's a little misleading, that arrow. We should say that we're substituting that here, because that's essentially what we're doing. We're leaving this lambda r alone. Although, no, we'll leave that as it is. But we could rearrange it if we want to at some point, I guess. We could substitute that into that lambda r as well, but it'll be useful to leave it as it is. Anyhow, if we do some massaging of this equation and we rearrange things and we simplify as much as we can, we'll get from this step into another step where we can say that, what do we say? We want to say that lambda r by dt. And so now you'll notice all of this is in terms of, well, not all of it. So we'll take it one step further after this. So this is j omega r minus omega s, well, just omega, because we've used omega. I was going to define omega s as the supply, but we can just leave it as omega. Plus 1 over tau r, and we've seen tau r before. Is e to the minus j rho minus lambda r. And this is is like that. And remember, this is can be expressed as isd plus j isq, right? We just saw this before. And if you forgot, then we can rewrite this as well, or we can come back and we can express this as well. This is tau r is defined as lm1 plus sigma r divided by rr. And they call this the rotor time constant. So this is the rotor time constant. Okay. Okay. Now we have here, essentially, we have real and imaginary components. If we equate all of the real components with all the real components, well, all the real components to the left side with the right side, and all of the imaginary component to the right side with the left side, you'll get two equations. And the result of these two equations is that, again, I'm not going to go through all the details because we'll be here forever if we do, but you get dimr dt is equal to minus 1 over tau r imr plus 1 over tau r isd. We can call this equation 9. And you get another equation where we can say omega slip, let's say, is equal to 1 over tau r isq imr. So this is what we call the slip frequency, or sorry, the slip speed, I guess you can say, angular velocity. Because what happens is the rotor, or the machine flux doesn't follow, doesn't exactly follow the supply. So you supply a certain frequency and it rotates at, again, if you have a frequency, it rotates in space at a fixed rate, but the machine flux is not able to perfectly follow that, basically. So the rotor flux, there's a difference between the supply and the rotor flux is essentially what this slip is describing. And it's usually small, but it's there nonetheless. So we can call this equation 10, and we can define omega slip as being equal to omega minus omega r. And omega, again, so this is omega is the supply frequency, and then this is the rotor flux angular frequency, or angular frequency is what we can call it. So with that, we can then model this, or this pair of equations, I guess, if you will. We can model these in a sort of block diagram format. And so you have your currents, ISD and ISQ. Let's say you have two currents coming in, because control is always much simpler to imagine when you have block diagrams. And why not draw some block diagrams? So, because we've done a lot of equations now. So we're going to have something like this. And what do we have at each one of these arrows? We have here ISD. We have here ISQ. The output of this thing is IMR. The output of this thing is omega slip. The output of this is omega, and the output of this is omega r. right? Right. We're missing one connection here. So this should look something like this. And you have 1 over tau rs plus 1 and 1 over tau r here. And this is a division block. And omega slip, if omega slip is equal to omega minus omega r, then that means omega should be equal to omega slip plus omega r based on this equation up here. So that's the pair of equations we have there. So the two things we control are this current and then this speed. Now, in a p-pole machine, so we looked at a two-pole machine. So in general, let's say we have a p-pole machine. So there are p poles in this machine. P is the number of poles. So in a p-pole machine, so if you have a p-pole machine, you have a couple of differences, and they're not very major differences. What you have is that the mechanical or the developed torque is equal to P over 2 times this TE, which is, I mean, I guess we can get like electrical torque. However you want to describe it, essentially, in this case, what you have is the torque is not the same that's developed there. So there's a factor of P over 2 that the machine can actually output. And omega r is equal to P over 2 omega m. And so this is how the machine output is related to the actual physical parameters of the rotor flux and the electrical components and such. So this is the relationship between the electrical and the mechanical components. So if then you have this block diagram plus this, in a general model of the p-pole machine, if you have a p-pole current-fed, let's say, induction machine, you would have the following. And this is the last thing we'll look at. And I know this has been a very dense video because there's a lot going on here, but this is a very dense topic, I guess. So you'll have a block here. And so you'll have 3 currents come in, let's say. And these 3 currents will be IA, IB, and IC. So there's a 3-phase currents coming in. You go from ABC to DQ. So this is your ABC to DQ frame transformation, and I'll link that in another video. We've looked at that already. Well, I guess it depends on which order you look at it in, but that video exists, and we will link that in the description in case you don't know how to apply the ABC to DQ transformation. So you have a block here. You have another one here. You have another one here, and so this is for the torque control, I guess. The full chain, I guess you can say. So here we have another block here, and like this. And again, all this is based off of the equations that we derive, right? And so we looked at in the past how to draw a block diagram model given a set of equations, and this is nothing more than that, I guess, just done at a very large, or not large scale, but more complicated scale, I guess. And of course you need this row to come back from here, like so, and this goes directly out here. And I believe I drew that a little too far forward, because it'll be a bit more convenient if I put it like this. So what's what? The output of your ABC to DQ transformation, as you may expect, is ISD and ISQ. Okay, now you feed ISD into this 1 over tau r s plus 1 block, as we've done at the top. So, I mean, we did this here. So I'm basically combining this with this and the torque equation to make a general larger model. So you multiply that with ISQ, and you multiply that by 3 over 2 Lm over 1 plus sigma r, and the output of that is TE. Now if you multiply all of that by P over 2, then the output of that is Tm. So this is how you generate a torque command, or this is the relationship, I guess, between the current and the torque in your induction machine. So if you want to drive a vehicle using the induction machine, this Tm is now your developed torque at the output of the machine, and this is how you model it. This is 1 over tau r. This is the division block, and so this is part of the same. We saw this at the top actually in the previous block. This is an integrator, and so you have here omega slip, you have here omega r, and you have here omega, and so the output of this is obviously rho, and so rho gets taken back here to the dq transformation, because if you remember, the dq frame needs to rotate at a speed that is, or well, it does rotate at a speed that is equal to the angular frequency, and this here is, I missed a block actually. That's rather unfortunate because this is a long line. Anyhow, so this here is the mechanical speed, omega m. We should stick to the same consistent colors, I guess. Omega m, and this is p over 2, and this is omega r at the input here, which is based on these relationships here. So this is for a current fed machine, but the thing is, machines are often voltage fed by some type of inverter, power electronic PWM inverter, but we'll need to adjust this model with equations that relate ISD and ISQ to the voltages VSA, VSB, and VSC, but we can do that at some other point. I mean, down the road, when we develop a complete, when we take this model one step further, I guess. This was a very packed video, so why don't we review what we've done? So we started with these equations we had from the previous video that we had established. We defined this new current. Based on this new current, we were able to decouple the current, or sorry, these two equations essentially. And so by doing that, we are now able to control the torque directly using ISD, and then we can control the speed using ISQ. And in case you didn't notice that, that's essentially what we do. I mean, we do all this fancy stuff in the middle, but at the end of it, when we come to these equations, you look at ISD goes straight here, and ISQ does play a role in TM, and there are techniques that we'll look at after to completely eliminate this altogether, in control at least, because I mean, you can have like feed forward terms and all that kind of stuff to cancel the effects of one channel on another, or one variable on another. But for now, this will suffice, I guess, because this is a big step forward from what we started with at least. So I hope this was helpful. If you have any questions, leave them in the comments below. I know we skipped over a lot of steps in like the mathematical derivations, so if you're confused about any of those, comment below and I'll try to respond to all of them if I can. Like and subscribe to support the channel, and we'll see you in the next one.